Here we are again. This is a continuation of the periodic table, and you really have to know the periodic table because the next chapter, I consider the most important chapter in high school chemistry, is bonding. So here we go, a little bit of review, and then we'll get to the newer stuff. So first of all, periodic table. Yep. These are groups. The groups go down. Don't forget. And the big deal is, why are all these elements in group 1 put in group 1? Because all the elements that are in group 1 have one valence electron in their outside shell. Every single one of them. Even hydrogen. Now, so the big deal is this. If you have the same number of valence electrons in the outside shell, you're in the same group or family. So this is group 1 because they all have one in the outside shell. Now, as we go down any group, it goes period 1, 2, 3, 4, 5, 6, 7. That's the same thing as an energy level or a shell. So every time we go down one element, we gain a shell of electrons. So obviously, the atomic radius, or the size of the atom, gets bigger as we go down any group. Any group, we go down. So, why are the elements in group 2 put in group 2? Because they've got 2 valence electrons. Every single one of them has 2 valence electrons, so they're in group 2. Now, these groups right here, I'll put a T there. They are called the transition metals. Those are the transition metals. And remember what we said before, they're very weird because they not only have one valence shell, they've got 2 overlapping valence shells, which gives them many charges. Remember, charges are oxidation states. And the other thing about the transition metals, their ions form colored solutions. So we're not going to talk about those too much right now. Next, so you remember, any group going down, they get bigger. Now, so the atomic radius gets bigger as we go down. So in group 15, bismuth is the biggest element. Now, the bigger the atom, the more metallic it is. So we said the biggest atom is right here. The biggest atom is francium. So if that's the biggest atom, that's the most metallic atom on the whole periodic table. Now, even in this group, it starts out non-metals and then it goes to semi-metals, but down here, bismuth is a metal. So the bigger the atom, the more metallic it gets. Now, over here in group 1 and group 2, they are never found alone in nature. Why? Because they're wickedly reactive. You put those in water and they blow up. So as we go down a group, they get more reactive. So obviously, francium not only is the largest metallic atom on the whole periodic table, it's the most reactive. Now, why would that be more reactive than sodium or lithium? Here's the reason. The easier it is to lose a valence electron for a metal, the more reactive it is. So look at the valence electron in francium is in the 7th shell. It's way out there. Very easy to get picked off. And remember, metals don't want to gain electrons, they want to lose them. So, francium is not only the largest metallic element, it's the most reactive metal on the whole periodic table. So, going down any group, you gain an energy level or a shell every time we go down. So, what's happening is the size gets bigger. Now, going across is really different. Going across an energy level or a shell. So, we'll go across this one. We'll go across energy level 2. Now watch how this works. If we're going across, if we go from lithium to beryllium to boron to carbon, we're not gaining a shell every time we go across. We are gaining one electron, one valence electron in the same shell. So if you think of it as a negative and positive magnet, here, lithium, we've got 3 protons, which are positive, and think about the valence electron. We have 1 valence electron, which is negative. We go to the next element, we've got 4 protons, which means the positive magnet got stronger, and we gained another negative electron in the same shell. So what's happening is, remember, nuclear charge is how many protons you have. The nuclear charge is going from 3 to 4 to 5 to 6 to 7. So the nuclear charge is increasing, but also the negative charge from the electrons is increasing. So you've got stronger positive, stronger negative. So what's going to happen as we go across? The nucleus is going to draw in the valence shell because we're getting more protons positive here. We're getting more electrons in the same shell. So as we go across any period, the nuclear charge draws in the valence shell. So take a wild guess what happens to size going across any period. It gets smaller. So the size going across gets smaller because the nuclear charge pulls in the valence shell. The most important thing to remember is we are gaining a valence electron every time we go across, not a whole shell. We are gaining a valence electron going across. So this stays in the same energy level it'll show. So, size. Atomic radius going down gets bigger because we gain a shell of electrons every time. Going across, the atomic radius gets smaller because the nuclear charge, or the number of protons, increases. The number of valence electrons increase, and it pulls in the valence shell. That's size. Now, the next thing we got to talk about is that one word, electronegativity. Electronegativity is the ability to attract electrons. So, look at all these are metals. Metals don't want to gain electrons. They want to lose them. So if electronegativity is the ability to attract electrons, metals probably got lousy electronegativities. So non-metals probably have higher because they want to gain them. So I will tell you this, the ability to attract electrons, all right? Well, the element with the best ability to attract electrons is this guy, fluorine. And I already talked about, I call him Rambo of all the elements because it has 7 in the outside shell. And remember, all these elements want to have almost all the elements want to have a stable octet, which means 8 in the outside shell. It's got 7 in the outside shell. It only needs 1 more, and it only has 2 shells. So fluorine is small. It only needs 1 electron, so it really is a strong electronegative element. It will rip off just about any element. So fluorine's electronegativity is the biggest at 4. Okay? That's the biggest one. Now, look at this next group, the noble gases. The noble gases, almost all of them, have a stable octet, which means 8 in the outside shell. That's what everybody's striving for. Almost every element wants 8 in the outside shell. There are a couple elements that don't need 8 in the outside shell because they want to look like helium with 2. So the elements that only need 2 in the first shell to become stable would be lithium, beryllium, boron, and carbon is a toss-up because carbon got 4 in the outside shell, so it either can gain 4 to have 8 or it can lose 4 and have 2 and look like helium. So remember, that's the setup. Every element on the periodic table wants to look like noble gas electron-wise. So, getting back to the noble gases, they don't want to gain or lose. So the ability to attract electrons, which is electronegativity, they don't have any. They don't have any electronegativity whatsoever because they don't want to gain. So the noble gases got no electronegativity. Fluorine has the highest with 4. Now, let's come way over here to this guy again, francium. As we go down a group, why would francium have less electronegativity than lithium or sodium? Well, first of all, remember, metals got lousy electronegativity because they don't want to gain electrons. But why would francium have the lousiest of all the metals? Because it's so big. All right? Lithium only has 2 shells. Sodium has 3. Francium got 7. So that valence electron is way out there. So this has a horrible electronegativity. I think it's around 0.7. That's the electronegativity of francium. Remember, fluorine has an electronegativity of 4. The noble gases have electronegativities. They don't have them. Now, remember I said these guys right here. B, S, I, G, E, A, S. So it's B, S, I, G, E, A, S, S, B, and T, E. They are like the demilitarized zone between the metals and the nonmetals. Okay? They act as a buffer zone. So they have properties of both metal and nonmetal. So these are called metalloids or semimetals. Now, talking about electronegativity, the ability to attract electrons, fluorine is the highest at 4. Noble gases got none because they don't want to attract. Francium's got 0.7. So if these have properties of both, they should be right in the middle for electronegativity, and they are. Most of these metalloids or semimetals have an electronegativity of 2, which is right in the middle between 0 and 4. Okay, so that is how electronegativity works. So going down any group, if the size of the atom gets bigger, the electronegativity gets worse because it's harder to attract electrons. If we're going across a period, and the size of the atoms are getting smaller, and we go to nonmetals which want to gain electrons, you know that the electronegativity going across increases dramatically. So now we know 2 trends. Size going down gets bigger. Electronegativity going down gets smaller. Size going across gets smaller, while the electronegativity going across gets larger. So those are 2 trends. Now we got to talk about something else. The next thing we have to talk about is this. The next thing we have to talk about is something called ionization energy. And the name kind of tells you what it does. Ion. So the ionization energy is just how much energy you need to rip off an electron and make an atom an ion. So how much energy you have to put into that atom to rip off an electron. That's ionization energy. And obviously, you want to go for the most loosely bound electron, which is in the outside shell. You don't want to go to try to rip off any electrons on the inside shells. That would be too difficult. All right? So, now, let's check this out. Ionization energy is energy needed to rip off an electron. So what elements on the periodic table would be the hardest to rip off? Well, it would be the most stable elements that don't want to be ripped off. So the hardest element of all the periodic table to be ripped off is this one. Now, why would helium have the absolute highest ionization energy, or energy they have to put in to rip off? Because first of all, helium's a noble gas. It's wickedly stable, and it has 2 in the first shell, and the first shell's near the nucleus. So the nucleus is holding those 2 electrons really tightly, and so that has the highest ionization energy. Nobody can pull off its electron. And these guys going down, the noble gases, have very high ionization energies. So does fluorine and oxygen, because they don't want to be ripped off. They want to gain. Now, the lowest ionization energy would be the biggest element that has its valence electrons the furthest away. Oh, well, I wonder who that is. This one again. Francium. Francium is the biggest element. It's only got 1 in the outside shell, so that one's the absolute easiest to rip off. The easiest of all. So that has the lowest ionization energy. These guys over here, helium, neon, fluorine, and oxygen, they have the highest. They don't want to be ripped off. Okay? So now, let's go back over here. And let's do this. I have NaCl, and then I have, let's just say, RbCl. So those are 2 compounds. Na wants to lose 1 electron, and so does rubidium. Chlorine wants to gain 1. So my question is this. If you were chlorine and you were energy efficient, which one of these metals in group 1 would be easier to rip off? In other words, which one of these metals would have the least amount of ionization energy so it could be ripped off easily? Well, let's see. So we have chlorine that wants to gain an electron, and then I ask for these 2. I ask for Na or Rb. So which one would chlorine rip off the easiest? In other words, which one would have the least amount of ionization energy to get its electron ripped off? Sodium or rubidium? Well, it would be rubidium, because rubidium, the valence electron is in the 5th shell. Not too much energy you need to put in to rip it off. Sodium, the valence electron's in the 3rd shell. So it would take a little bit more energy, a little bit more ionization energy to rip off sodium than rubidium. So here's what's going on with ionization energy. Here's the pattern. As the size of the atom gets bigger, you need less ionization energy to rip off that electron. So as we go down any group, the ionization energy decreases. But if we're going across a period, the size of the atoms are getting smaller and smaller and smaller, so that the valence electrons are closer to the nucleus. So the ionization energy going across gets larger and larger and larger. And finally, we get to around here. These elements right there, they're the smallest elements. They want to gain electrons, the oxygen, fluorine, sulfur, and chlorine. And then we have the noble gases. They have the highest ionization energy. In other words, once again, that would take the most amount of energy to make them ions. And that means if you wanted to try to rip them off, you'd have to put in a ton of ionization energy to rip them off. Okay? So ionization energy, energy necessary to rip off the most loosely bound valence electron. That's ionization energy. So now watch. Mostly these properties depend on size. As we go down a group, the size gets bigger. If the size gets bigger, the ability to attract electrons, electronegativity, gets smaller. The amount of energy you need to rip off the electrons gets smaller. So going down a group, as size goes up, electronegativity and ionization decrease. as we go across a period, size gets smaller. So the ability to attract electrons gets higher, and the amount of energy needed to rip off those electrons gets higher. So as we go across, the size gets smaller, but electronegativity goes up and ionization energy goes up. Okay? So these are three big ones: atomic radius, electronegativity, and ionization energy. Now, the next thing we have to talk about is we have to talk about the groups. So, we already said that group 1, all the elements in group 1 are in group 1 because they only have one valence electron. And I said before in a previous video, hydrogen is in group 1, but it's split off. It's split off because hydrogen's a gas, and these are metals. But it's still put in group 1 because it's got one valence electron. Now, interesting, group 1, group 2, and group 17. Remember, group 17 is called this. The halogens, group 1, group 2, and group 17, those elements are never ever found in nature by themselves because they're too reactive. Remember what I said, group 1 and 2, you put them in water, they blow up. In fact, if you put group 1 in water, it changes the shape of the metal. So, group 1 and 2 and 17, they are never found in nature by themselves. Well, then how do we get them alone? We find them in compounds, and we chemically break them apart. Not physically, we chemically break them apart so we can get the group 1, group 2, and group 17 elements by themselves. All right. Now, the next thing we have to talk about, the electron dot of all these elements. So the electron dot of group 1, well, it's got one valence electron. So there's the one valence electron. The electron dot of group 2, remember group 2, it would be an S2. So this would be an S1. This would be an S2. Then we come over here to group 13. Group 13 means it got three valence electrons. So it's S2, P1. Carbon, weird one. Group 14 got 4 electrons. It should look like this, S2, P2. But carbon does not look like that. Carbon, this S electron jumps into the P subshell. So it's right here. So now, carbon, the only element up there in group 14, has electron at 12, electron at 3, electron at 6, and electron at 9. Okay, all the rest of them have a pair on top and 2 singles. All right, let's go to nitrogen, or group 15. Group 15, that means it has 5 electrons in the outside shell, S2P3. So it looks like this, S2, pair, P3, there's P1, there's P2, there's P3. So that's nitrogen. Oxygen, 6 in the outside shell. So that means an S2P4. There's my S2, P1, P2, P3, and P4. So that is what any element in group 16 looks like. 2 pairs and 2 singles. Group 17. S2P5. So, it's got a pair for S2, single, 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 pair, pair. So now, anything in group 17 has got 3 pairs and 1 single. And finally, we get to the noble gases. And all the noble gases except helium has a stable octet, which means it's got 8 in the outside shell. So 8 in the outside shell would look like this. Pair, 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 pair. And don't forget, helium would just have a pair on top. So that is the electron dot of groups 1, 2, 13, 14, 15, 16, 17, and 18. All right? So in the next video, we will talk about the properties of each group. And then we'll talk a little bit about the properties of the periods. Then we'll talk about general properties of metals, general properties of nonmetals, and then we'll just about be finished with this super important periodic table chapter. All right, thanks.